Hello everybody, welcome to 4-5 Solving Rational Equations. This will be the last lesson in the unit, and we're finally going to actually solve some stuff instead of just simplifying expressions and factoring. Alright, so let's start with some basic ones. If we go here, our first problem says solve for x, and we're giving the equation 10 over x plus 4 equals 2. Now, if you're one of those people that kind of looks at a problem, tries to figure it out real quick, if we know that this whole left-hand side has to equal 2, well, 10 over 5 equals 2. And in order for the denominator to be 5, x has to be 1. So we know the answer is 1. But let's go ahead and do a basic algebra problem and kind of rearrange this a little bit just so we can show how we would do this if the numbers are not so easy. So if we have 10 over x plus 4 equals 2, I'm going to actually leave some space here, because what we're going to want to do is we're going to want to get the x plus 4 out of the denominator, and the way we're going to do that is by multiplying both sides by x plus 4. So we'll multiply this side also by x plus 4. And of course, these will cancel on the top and bottom, and we'll get 10 equals, if we distribute the 2, we'll get 2x plus 8. And now we can solve from here. So we subtract 8 from both sides, minus 8, and we get 2 equals 2x, which of course means x equals 1. And we already kind of knew that, but hey, we showed how we can basically multiply both sides by the denominator to get x out of the denominator, and then just simplify it from there. All right, so that was like an easy method. These methods can actually get a bit crazy if you want them to. You can always just stick to the method before. I thought I would just show you something kind of cool that works kind of in the same way. Although in this case, when we have a 1 in the numerator, it's not really as fun. We'd kind of have to use the same method. So, but the idea behind this is if I want to, if I have my initial, let's just do this here. So 1 over x minus 3. And then on this side, I'm just going to write like 5 over 1. Essentially what we can do, and we could have done this before, like I said, the only reason why this one's a bit odd is because the number up top is a 1. But we can multiply both sides by the reciprocal of the side that has the x in the denominator. So if we multiply this one also by x minus 3, you'll see that this is the same idea, right? X plus minus 3 over 1. And now these two things will cancel. These two things will cancel. And essentially what we'll just get on this side is just a 1, right? Because all this multiplied by each other is just 1. And 1 is going to equal, well, 5 times x minus 3. So 5x minus 15. And now we can add 15 to both sides. Plus 15, and we'll get 16 equals 5x, and divide by 5, and we get x equals 16 over 5, which can't really be reduced. Right? What, 3 1/5? Cool. I will leave the apply for you guys. Go ahead and give it a shot, and if you'd like to, you can go ahead and pause the video, go ahead and give that a shot, and yeah, just see if you can follow along with the same pattern there. All right, so we're going to get into a word problem. Then we're going to go back into some math, just more like basic like practice problems. And then we're going to get into a more challenging application here at the end. All right, so let's go ahead and talk about rates. Now, in this case, this one is more specifically known as a work rate, but there's tons of different rates, right? If we talk about, for instance, a rate of pay, how much are you paid? Well, you're paid an amount over an amount of time. You're paid $30 per hour, or you're paid, $60 a month, or something like that. Well, the last one would be pretty bad, but you get what I mean, right? So you're paid a total amount of pay over time. Let's talk about a rate of speed, right? How fast are you going? Well, you're going your distance over your time. So you'll notice that in almost all rates, what a rate is it's the thing we're measuring or the thing we're collecting over how long it takes us to collect that thing, right? So we're collecting distance, and we're determining how fast we're going based on how much distance we collect over how much time. So anytime we're talking about work, we're talking about the same idea. How much work can we do in how much time, or divided by how much time? It's the same concept. So let's go ahead and look at a problem here. All right, so Arthur and Cheyenne are making Chinese paper cutting designs. Together they can complete the job in 24 hours. If Cheyenne works twice as fast as Arthur, how long would it take for her to complete the task herself? Now, of course, the rate of work is the number of jobs, or how much work you can do, over the amount of hours that you worked. So let's go ahead and think of what these would look like, right? So first of all, for Arthur, the number of jobs he can achieve and how much hours he worked. Well, let's say we don't know how many hours he worked, right? Because that's literally the thing we don't know. All we know is that Cheyenne works twice as fast. So there's a couple ways we could look at this. We could say that Arthur and Cheyenne both do one job, but that Cheyenne takes half as long, right? The other way we can do this, which will be a little bit easier so that we can get the same kind of denominator, is we can say that Arthur does one job in X amount of time in the same amount of time that Cheyenne could do two jobs in the X amount of time, right? So we could write this like this. In theory, we could also say Arthur does one job, right, over X, and then we could say that Cheyenne does one job over like 0.5x because it takes her half the amount of time, right? So we could look at it either way. But this is probably the easiest way to do it, right? And we know that the total job takes 24 hours. So if the total job, like the actual job itself, we can create like a third category here. We know we're going to do one job in 24 hours, right? So we know that Arthur's rate plus Cheyenne's rate is going to equal the total job. So we can actually do this like this. We have 1 over x plus 2 over x equals 1 over 24. Which kind of takes us to, how do we start this problem? Well, we need to get x out of the denominator, right? And the easiest way to think of this is to find the LCD. You'll remember the LCD from the last lesson, and the way we do this is we take the factors of everything in the denominator, and we find everything unique, and we find the thing that's the most. So in each of these, an x is going to be unique, and quite frankly, a 24 is going to be unique, right? So we have 24, x is going to be our LCD. So what we're going to do is we're going to turn every piece of the denominator into the same piece. That way we can use the rules of adding fractions to our advantage, right? So what are we going to have to do to turn this bottom piece into 24x? Well, it's 1 over x, right? So we're starting here on this piece. In order to get this x on the bottom to be a 24x, we have to multiply the top and bottom by 24. So that's exactly what we're going to do. This is going to turn into 24 over 24x. And it looks a little strange, but it'll make sense here in a second, right? Now for this one, we have an x on the bottom, right? Exact same thing. If we have an x on the bottom, we need it to become a 24x. So we're just going to have to multiply the top and bottom by 24. So 2 over x is going to become, well, 2 times 24 is 48, right? So 48 over 24x. And this is going to equal, well, this already has a 1, right? Or a 24 down here. So now to make this 24x, we have to multiply both sides by x. So what we're going to do is this is going to become 1x, in other words, just x, right, over 24x. And now what's cool is, let's think about, if we just had a basic fraction, right? Let's say I had an equation that said like 1 over 3 plus x over 3 equals 4 over 3, right? If I gave you a problem that looked like this, you'd say, well, Mr. Moneypenny, if I have 1 plus x equals 4, right, I know x has to be 3 because I can just add across the top because my denominators are the same. Well, that's the same thing we're going to go here, right? We're going to almost ignore the fact that the denominator exists now. Once we have the denominator the same across the board, we can borderline pretend it doesn't exist and just move on. So what we're going to have is we're going to have 24 plus 48 equals x. Right? Okay, so let's solve for this. 24 plus 48 is going to give us 72. And 72 equals x. So if we do one job over x hours, right, that's Arthur's rate. So how long would it take for her to complete her task herself? So we're talking about Cheyenne. So if it takes Arthur 72 hours to do it, then Cheyenne's going to take half that amount, right? 2 over 72. And 2 over 72 is the same as 36. So we know that Cheyenne is going to take 36 hours. And that's it, right? So what we did is we established what a rate of work is. We knew that Arthur was one rate, or was one job per however much time. We don't know the amount of time. We said that Cheyenne could do 2 jobs in that same amount of time, right? Because it takes her half as long to complete each task. So in the same amount of time, she can complete 2 tasks. And then we know that the total job, which is one job, right, is going to take 24 hours. So we set up both of their rates add up to the 24. And then we found the LCD, which was 24x. We turned all of these fractions into something with the same denominator, and then we just added across. So we have 24 plus 48 equals x. And if x is the amount of time it takes to do those jobs, well, Cheyenne can do 2 jobs in 72 hours, which is 36 hours per job. All right. So far, so good. Let's go and do one more. Kind of a similar problem. What I would recommend is for you to kind of pause the video here and try to set it up yourself. See how far you can get into it. And once you get stuck, just stop and follow along with me doing it here. So I'll give you like 2 seconds here, and then we'll go into it together. All right, so let's go ahead and get back into this. So, okay, it takes 12 hours to fill a pool with 2 pipes, where the water from one pipe flows 3 times as fast as the other. How long would it take for this lower pipe to fill the pool by itself? Well, the same thing, right? Our rate of work is going to be the number of jobs. So we have number of jobs divided by the time it takes, which in this case is in 3 times as fast. Yeah, hours. So time is in hours, right? Up here at the very top thing, it says it takes 12 hours. So let's call pipe number 1. We'll just say the pipe number 1 is the slower pipe, right? So it takes 12 hours to fill a pool with 2 pipes, where the water from pipe 1 flows 3 times as fast. So basically, if pipe 1 takes 1 for the one job takes X hours, then the next pipe, the faster pipe, could do 3 jobs in that same amount of time, right? So this is we could call this like the slow pipe, is this one here, right? And then this one is like the faster one, like the one that can go just can do a little bit more. And then it takes 12 hours to fill the pool with both pipes. So if this is the case, well, they can do 1 job, and they can do that in 12 hours, right? So here, the first one, the slow one, we can do 1 job in X amount of hours. The fast one can do 3 jobs in that same amount of time, and our job combined our 1 job is going to take 12 hours. So now let's find the LCD, just like we did before. So here I have a bunch of X's on the bottom, and here I have a 12. The only real LCD is just to kind of multiply these together, which does happen quite often with fractions. So our LCD is 12x. So now let's go ahead and turn each of these fractions into something with the same LCD at the bottom. So here I have 1 over x. In order to get this x to become 12x, I have to multiply it by 12. So 12x is on the bottom, and then we multiply the top by 12. 1 times 12 is just 12. All right, so in order to make this one a 12x, we have an x on the bottom, so plus, so we have to multiply top and bottom by 12. So plus 12x, we multiply the top by 12. 3 times 12 is 36. Okay, and the last one, we have a 12, but we need it to be a 12x, so we have to multiply the top and bottom by x. So we have x over 12x. And now remember, because we have a fraction, and we have all the denominators are the same, we can just add across the top. So we know 12 plus 36 equals x. So we know that x equals 48. And of course, x is the amount of time it takes to do, or x is the values down here, right? So for the slow one, it's the amount of time it takes to do 1. For the fast, it's the amount of time it takes 3. So what's our problem asking? How long would it take the slower pipe to fill the pool by itself? Well, the slow pipe is 1 job per our x, which is 48. So it would just take it 48 hours. So that's our answer. So the slow pipe would take 48 hours. And if you're wondering, the fast pipe, right? The fast pipe would be 3 over 48, and 48 divided by 3 is 16. So the faster pipe, we could do in 16 hours. Cool. All right, fun stuff. So now let's go up to finding extraneous solutions. Now the word extraneous just basically means extra, unnecessary, that sort of thing. In this case, it's going to relate to us solving for x, and then once we've solved for x, we are going to find which answers don't actually make sense. Kind of like, do you remember when we did quadratics and we said, oh, a person throws a ball or hits a golf ball from a platform and then it lands, and you'd get answers like -3 and +5. And it's like, how long would it take for it to reach the ground? Well, it can't reach the ground in -3 seconds, right? So that would be an extraneous solution. So something like that, only in this case, we're going to use our domain to establish a range of answers that are not possible, just like we did with when we established a domain in the past. All right, so let's go and jump into this. So if we're identifying extraneous solutions, first thing we have to do is actually solve for x. And x is we're going to solve for x kind of like we did in the last problem, where we're going to establish an LCD and we're going to go from there. So let's just look at this. Okay, we're going to go step by step. So if we have a problem, 1 over x minus 5 plus x over x minus 3 equals 2 over the quantity x squared minus 8x plus 15. Okay, so step 1 says factor everything. All right, well, let's do it. There's not really much to factor in this case, right? So we have 1 over x minus 5. There's literally nothing to factor there. And then plus x over x minus 3. Again, nothing to factor. X minus 3. And this is going to equal 2 over something we can factor. You didn't think there was going to be no fun, did you? All right. So x squared minus 8x plus 15. What can we use that multiplies to get 15 that adds together to equal -8? Well, -3 and -5 would do the trick, right? So let's do it. So x minus 3, x minus 5. All right, so now we've factored everything. All right, now multiply by the LCD. Now this was when we were just evaluating expressions, we already did this, right? So the first step is to figure out what the LCD is. If I look at the different expressions up here, I have an x minus 5 in the denominator, an x minus 3 in the denominator, and then this one has an x minus 3 and an x minus 5. The LCD is just going to be the same as this last expression here, which is just going to combine both pieces. So the LCD is x minus 3 times x minus 5. And of course, that is including all unique factors, and it's including the most of each unique factor, right? There's only one of each in all of these, so the one is also the most while being unique. All right, and now what we're going to do is we're going to take each of these expressions and we're going to multiply it by what's necessary in order to make the LCD. So in other words, let's just look at this first one, right? We have 1 over x minus 5. Well, in the denominator, what are we missing? We have an x minus 5. We're missing this x minus 3. So what we're going to do with this first one, here, I'll rewrite it just for the sake of making this a little bit more straightforward, right? So we have 1 over x minus 5. We have to multiply the top and bottom by x minus 3. So this is going to become x minus 3, because it's just x minus 3 times 1, right? Over x minus 5 times the x minus 3. So we're multiplying the top and bottom of this one by x minus 3, so that way we can have the same denominator across the board. All right. All right, next one. So plus, and over here we had x over x minus 3. So plus this. Now here we already have the x minus 3, right? But we need the x minus 5, so we're going to multiply the top and bottom by x minus 5. So here we'll have x times x minus 5 over, we already had the x minus 3, right? So now we have the same LCD. So we have x minus 5, that's what we had to multiply by, and then it already had the x minus 3. So we have the same denominator here, and now our final piece is this one, which is 2 over x minus 3 times x minus 5. The LCD is already exactly what we want it, so we literally don't have to change this one at all. So 2 over x minus 5 times x minus 3. Okay, perfect. So now we have our expression where we've taken the LCD, and the important thing that this second step did is it made us that all of our denominators are the same. And just like we did in these other problems, right? Once we know that we have 1/3 plus x over 3, right, equals 4, we can say 1 plus x equals 4. Because the denominators no longer matter, because as long as the denominators are the same, we can kind of just use the numerator to solve the problem. So that's what we're going to do here. Use the numerator to create an equation. Well, let's just do exactly what we did, right? We can ignore the denominators, basically. So we have x minus 3 plus x times the quantity x minus 5, and that's going to equal 2. So let's go ahead and use the distributive property. We have x minus 3 plus x squared minus 5x equals 2. Now we're going to combine some like terms here. So I have an x and a negative 5x. We can use some color here. It's always fun when combining like terms. So we have an x and a negative 5x. And then everything else is just kind of their own terms. So we'll have a x squared x minus 5x is minus 4x. And then minus 3. All right. And then, cool. So we use the numerator to set up an equation. So this all equals 2. And now for the last step, we're going to solve for x by setting it equal to 0. So here we have x squared minus 4x minus 3 equals 0, or equals 2. If we were to get rid of this 2, we would have to subtract 2 from both sides. So if we subtract 2 over here and subtract 2 over here, then what we're going to get is x squared minus 4x minus 5 equals 0. All right. But we have to solve for x, right? Like the whole point of this problem is to solve for x. Well, here we have something we can factor, and then once we factor, we have a quadratic. We can set everything equal to 0, and we can solve for x. So let's go ahead and do that. So really the question here is what multiplies to make negative 5 that adds together to make negative 4? And the answer, of course, is negative 5 and positive 1. So x minus 5 times x plus 1. And of course, this would FOIL back into this, right? This is how we factor trinomials. And this all equals 0. Now, just to be clear, and I've explained this many times before, but I just want to make sure we're clear. Let's say if this was like a, right? If this little piece was a and this little piece was b and this equaled 0, if we said a times b equals 0, one of these pieces would have to equal 0, right? In other words, if a was 1 and b was 3, we'd get 3, right? Not 0. In order for the answer to equal 0, one of these pieces has to be 0. So what we can do is, using that logic, we can say that x minus 5 equals 0 and x plus 1 equals 0. So now we just kind of solve for x, and you'll notice that's just kind of the opposite, right? So I'd add 5 to both sides, and I would get x equals 5. And then on here, I have plus 1, so I would subtract, so negative 1. So x equals 5 and negative 1. Cool. We solved for x. If you plug in a 5 and a negative 1 at any point here, right, it would look like we're good, right? Like, okay, if we plug in x here, we're fine. But the problem is that, yeah, our answers look good here, but that's because we were largely ignoring the denominator. So if we go back up here, if we look at this first problem, you'll notice that just like when we do our domains, what would happen here if x was a 5? Or what would happen if x was a 3, right? If x is a 5 or a 3, we're going to get a 0 in the denominator. And that is not a good thing. That doesn't work for us, right? So in other words, the answer of 5 and the answer of 3, right? If we look at our factored form here, it's a little bit easier. The answer of 5 and the answer of 3, and then of course over here, 3 and 5 again. 3 and 5 cannot be a part of the solution. So when we go back down here, right, we set our answer as x equals 5, x equals negative 1. But we know that our extraneous solution, in other words, the answers that cannot be possible, the answers cannot be, it cannot be 5 and it cannot be 3, right? Again, if we go back up here, we can see this, x minus 3x plus 5, or x minus 5. If we were to plug in a 3 here, we'd get a 0. If we were to plug in a 5 here, we'd get a 0. We can't get a 0 in the denominator. So these answers are impossible, which means that our only actual answer is x equals negative 1. That's the answer. This is the only thing you can plug in all the way up here. It's the only one you can plug in all the way up here and actually get an answer where this side will equal this side and it doesn't have a 0 in the denominator. It's the only answer that works. So you can go ahead and give that a shot if you want to like try and plug it back in and see. But all right. So again, we're at that practice step. So what I'm going to let you guys do is pause the video. If you guys want to try this, I would strongly suggest it. Go through the steps, give it a shot. If you get stuck, you get stuck. That's why it's a video, right? You can always unpause it, watch me do it, and then go back and fix it and be like, oh, look what I did. So go ahead and take a second and pause the video and give it a shot. And when we get back, we'll do it together. All right, so let's go ahead and jump into this one. We're going to do the exact same thing we did before. Step 1 is factor everything. Now, what's amazing is literally nothing needs factored. Actually, in the original problem, this was just a giant 7. I went ahead and put it as 7 over 1 because you're going to want to be able to match up the denominators, right? If we go back up here, first thing was factor everything. Well, we kind of did that. So now we're going to find the LCD, and then once we find the LCD, we're just going to set up an equation. So let's do it. So LCD, I have x minus 2, I have a 1, and I have an x minus 2. The only possible LCD here is just to multiply everything together. And fortunately, multiplying things by 1 doesn't really do anything. So our LCD is simply x minus 2. Okay, cool. So this first part here, 5x over x minus 2, that's not going to change, right? Because there's already an x minus 2 in the denominator. So that's it. All right, so that one just kind of stayed the same because we already have what we want. Now, 7 over 1 does not have an x minus 2 in the denominator, so we have to turn it into that. So in order to do that, we have to multiply the top and bottom by x minus 2. So this will become 7 times x minus 2 over x minus 2. All right, cool. Now we have an x minus 2 in the denominator. We're good. This last one is the exact same, right, as the first one. We have an x minus 2 in the denominator, so we don't have to do anything, which is always nice. Makes our life easy. All right, and now all of our denominators are the same, which means we can set up an equation with just the numerators. So we know that 5x equals 7 times the quantity x minus 2. And this is going to be plus 10. All right, now let's distribute. We're going to get 7x minus 14 plus 10 equals 5x. And we're trying to set this equal to 0 ultimately as well, remember. So let's go ahead and do this. So we have, let's see. We'll go ahead and add negative 14 and 10. We're going to get negative 4. So 7x minus 4 equals 5x. We'll minus 5x. And we'll get 0 equals 2x minus 4. Oh, so this isn't even a quadratic. I guess this step actually didn't make much sense. I should have just subtracted 7 from both sides, right? That's fine. Well, so normally if this was a quadratic, right, because we'd have like x times x somewhere, right? We'd have to multiply x's. If we have a quadratic, then we do have to set it equal to 0. In this case, we really don't. So let's just go ahead and do this. So I'm going to add 4 to both sides. Kind of did an extra step here for no reason. That's fine. So now if I bring this back up here, I've got 4 equals 2x divided by 2, divided by 2, and of course x equals 2. Awesome, right? Okay, so we solved for x. Now, let's look back at the initial problem and see if there's anything wrong with this. Okay, let's look at it. So we have 5x over x minus 2. Ooh, do you guys see the problem? What happens if x equals 2? It doesn't work. Well, Mr. Moneypenny, that was our only answer. So what does that mean? Are you telling me there's no answer to this problem? Guess what? Yeah, that's what I'm saying. There's no answer to this problem, right? In fact, let's think about this for a second. If I was going to plug this into a graph, right? If I was going to solve by graphing, what I would do is I would put everything on this side of the equation on one graph. I would put everything on this side of the equation on the other graph, and then all I would do is just look at the graph and say, okay, where do they cross, right? Wherever they intersect, that's the solution to the problem, right? If only there was a way to graph really easily, that would be really cool. Oh my gosh, there is. Let's do it. This is the moment that I've been waiting for. Oh, wrong thing. All right, so 5x over x minus 2 is our first one. So 5x over x minus 2. And then for the second one, we're gonna put the other one over here. So 7 plus 10 over x minus 2. 7 plus 10 over x minus 2. So 7 plus 10 over x minus 2. Okay, just to double check, 5x over x minus 2, 7 plus 10 over x minus 2. Okay, yeah, everything looks good. All right, now let's zoom out. Oh, where do they intersect? Oh, well, surely they intersect here, right? Look at this. Look, they gotta intersect, right? Right? Clearly. No, they don't. They literally never do. They just kind of sit side by side forever. Yeah, that's just all that's all that's ever going to happen. It really looks like they want to cross, but they don't. And then the same thing's true up here. It's the exact same thing, just on the other side. As you zoom in, you'll see it never crosses. So what's the solution to this? Well, there isn't one, right? The only possibility was two, and we see what happens there, right? In fact, we really see what happens there. Where's two? Right here. Look at what they're approaching but never touching. It's two, right? We have an asymptote. Of course we do. All right. Awesome. That was a lot of fun, right? We got to see how much work we could do literally to solve nothing, which was kind of nice. All right. Solve rate problems. Here we go. So this one's pretty challenging, but I think it's got a lot of really, really instructive things here. So let's go and jump into it. So paddling with the current in a river, Jake traveled 16 miles. Even though he paddled upstream for an hour longer than he paddled downstream, Jake could only travel 16 miles. If Jake can paddle at a rate of 5 miles per hour in still waters, what is the speed of the current of the river? Get rid of this extraneous can paddle. All right. So let's think about what this means. Okay, first of all, what is the speed of the current of the water? Well, the speed is a rate, right? And our speed is always the distance over time, which in this case, we're talking about miles per hour, right? That's usually how speed is determined. But there's a few things that are important here. And this is, I think, the key takeaway from this problem, because if you don't really understand what a current is or what upstream or downstream or anything like that mean, this problem is going to be impossible to solve, right? You have to be able to look at this problem and go, if I'm paddling with the current of the river, right, am I going to go faster or slower? Well, if the current is pushing me forward, I'm going to travel faster. So it's however fast I can push plus the speed the water can push me, right? And then if you're traveling upstream, right? Upstream is the term for traveling against the current. If the current is pushing against you, it's going to be how fast you can push minus how fast the current is pushing against you, right? So in this case, Jake is trying to he's traveling in a river, right? And he paddled upstream for an hour longer than he paddled downstream. So in this case, if we look at this, right, we're going to let the current of the river equal c, because that's the thing we don't know. We know the current. We know Jake can paddle at a rate of 5 miles an hour, right? So we know how fast Jake can do it. We also know how far he traveled total, right? We know the amount of time. The only thing we really don't know in this case is the current of the river, which is, in this case, like the challenging part of the problem. All right. So in this case, let's look at our distance for let's look at our distance for when we're traveling upstream, right? So in other words, this is when we're fighting against the current, because we're gonna need both of them, right? Because essentially, if Jake can paddle at a rate of 5 miles in still waters, what is the speed of the current of the river? Well, what we're gonna have to do is we're gonna have to compare the current when Jake was traveling downstream, and we're gonna have to compare Jake when he was traveling upstream, and we're gonna be able to set those up so that they both have a c, and then we can kind of use that to solve for c, and that's how we'll know the speed of the current, right? So the first thing we're going to have to do is we're going to have to think, okay, well, we're doing distance over time, right? Speed is distance over time. Well, the time it's going to take is going to be depending on the current, right? And we know that Jake's speed minus the speed of the current is going to be how long it's going to take for us to go upstream, right? So it says here, Jake traveled 16 miles. Although he paddled upstream for an hour longer than he paddled downstream, Jake could only travel 16 miles. If Jake can paddle at a rate of 5 miles per hour in still waters, what happened to the speed of the current? Or what is the speed of the current of the water? All right. So, this is supposed to be a 6. My bad. That would kind of ruin the problem. It's like, yeah, we know he can travel 60 miles. All right. So, even though he paddled longer upstream, right? But he could only travel 6 miles, even though he was doing it for an hour longer. So basically what this means is that on this side, well, what's the distance? Well, we traveled 6 miles over, well, what's our time? Well, here we're actually trying to find the rate, right? So our rate is actually, like we said, is going to be Jake's rate minus the rate of the river, right? Which is the thing we don't know. So if we know that Jake's rate is 5 miles per hour, then what we can actually do is we can put 5 minus c. And just to be clear, right, if we know speed, right, speed is our rate. We'll just call it rate in this case, just to kind of give you the idea. If rate equals distance over time, and we're trying to find the time, right, then we can solve for time kind of by just switching these, right? I know we've done problems like this a lot. You'd multiply time by both sides, and you'd get rate times time equals distance, and then you divide by rate. So what this is going to turn into is it's going to turn into time equals distance divided by rate. And that's kind of what we're trying to do here, right? Over here we have our time, so we have our hours, and then here we have our speed, right? Our rate. Our rate is 5 minus whatever that current is. All right. Now, remember, this is the time that he was traveling upstream, right? Upstream, he traveled 6, right? Or this is distance. I don't know why I put each for hours. This is actually in miles, right? So this is our distance. Our distance divided by, right? If we look over here, distance divided by rate. Our time is our distance, which is 6, divided by our rate. So this is upstream, right? This is the little equation for our upstream. All right, our distance for downstream is going to be a little bit different. Well, it's the time, right? So if we're comparing to this, you'll notice the first thing it says here is, even though he paddled upstream for an hour longer, so this time is actually an hour more. So to make them equal, we're going to actually have to add 1 over here, right? So this is going to be 1 plus because the time is 1 extra, right, over here. Well, it's actually 1 extra on this side, right? And so in order to make it equal, we have to add the 1 here to accommodate for that. And then we have distance divided by rate, right? So our distance is, in this case, well, we actually were able to travel 16 miles, right? When he traveled with the current of the river, he traveled 16 miles. So we have 16 over. Well, in this case, we're talking about the rate when we're flowing with the river. So if we're flowing with the river, we're going to add Jake's rate plus whatever the current is. So in this case, it would be 5, which is Jake's rate, plus the current. Right? So now we have an equation where we can solve for C. Okay? So let's go and do this. So we have 6, or first of all, we have to find LCD, right? First of all, factor everything. There's nothing really to factor in this case. So now we do LCD. And our LCD is going to be 5 minus C times 5 plus C. It's really the only things that we have in the denominator. The only other thing is a 1, so that's not really going to do anything for us. 5 minus C, 5 plus C. All right, so now let's go and do that. So we're going to take every individual piece, and we're going to do that just like we did before. Let's take these down. All right. And we might get some big numbers here, but that's fine. We can figure it out. So let's go and get started. So we have 6 over 5 minus C. So this is going to be, well, if we have a 5 minus C on the bottom, we need to have our 5 plus C as well. So I'm going to get 6 times 5 plus C over 5 minus C times 5 plus C. Okay. Now the 1 over 1, we're going to have to take everything, right? 5 minus C and 5 plus C, and there's not really a way to get around it. So 1 over 1 is just going to become 5 minus C times 5 plus C over the same thing, 5 minus C times 5 plus C. And finally, plus, we have 5 minus, or plus C on the bottom, so we're going to have to multiply by both by 5 minus C. So we have 16 times 5 minus C over 5 minus C, 5 plus C. Okay. So now we have all the denominators the same, just like we did before. So what we are going to do is we're going to go ahead and just set up an equation on top, because we know that this has to equal this plus this. So we have 6. Go ahead and move up here. I have 6 times 5 plus c equals 5 minus c, 5 plus c. And then plus 16 times 5 minus c. Okay, so let's simplify some stuff. We have 6 times 5 is 30. 30 plus 6c equals, all right, 5 times 5 is 25. Plus 5c, whoop, that's just a c. And we know these are going to cancel out. Hopefully you notice this is kind of like a difference of squares pattern, but it's fine if you don't right away. So plus 5c minus 5c, which again, this here is all just going to cancel out, which is fine. And then negative c plus c is negative c squared. All right, we just FOILed those. And then plus 16 times 5 is 80 minus 16c. All right, so now we have a lot of pieces. So I'm going to just scratch these out first. Might as well not even deal with those if we don't have to, right? So here I have a 25 and an 80, and then it looks like the other pieces are just the same. So let's go ahead and simplify this side first. So if I have 25 and 80, then that's going to give me 105. So I'll have negative c squared minus 16c plus 105. Okay, so far so good. Now we're going to try and set this equal to 0. So what I'm going to do is on this side, I'm going to subtract 30, and we have a plus 6c, so we're going to minus 6c. So over here, so I'm going to minus 30, and I'm going to minus 6c, and I'm going to get negative c squared. Well, first of all, this is all equal to 0 now, right? Negative c squared minus 16, so this is what, 22c? And then this would be plus 75. So what I'm going to do now is I'm going to take a negative out of all of this just to make it a little bit easier for me to do. So let's just go right back up here. So we're going to get 0 equals, if I multiply both sides by negative 1, it's going to be 0 equals c squared plus 22c minus 75. We're so close, guys. We're so close. All right. Now, a little bit of math here. What multiplies to make negative 75 that adds to make positive 22? Now, the only numbers I really know for 75 off the top of my head are, I know it's 3 times 25, and then it's, 7 times 15, I think? The one I know off the top of my head is 3 and 25, right? I noticed that if I multiply positive 25 and negative 3, I'll get this number. So that's what my numbers are. So positive 25 and negative 3 will work. So 0 equals c plus 25. Whoop, wrong button. C plus 25, c minus 3, which is of course going to give me c equals negative 25 and 3. All right, now here's the question, right? The current of the river, right, is how hard the river is pushing. Does that make sense? So if we're looking at this, is it possible that the current could be pushing a negative amount? Like, in other words, is the rate of our current, because this isn't just the current, it's the rate of our current, right? It's how much is the river like pushing, which a component of that is time, right? Is it possible for the current to be pushing us in a negative pace? I guess is what I'm saying. Like, can the current be negatively pushing us? Well, we can be going against a positive current, right? But that's not the same thing as the current providing like a negative pace. So it's actually not possible that C could be negative 25, right? A current can't be negative. So the current, in this case, the speed of the current, because like I said, you can't be going negative 25 miles an hour, right? That doesn't make any sense. So 3 is actually our answer. So the speed of the current is 3 miles per hour. It was a lot of math, right? A lot of understanding. I'll go over it real quick again, okay? And then the next problem is actually complicated and involved just like this. So if you're feeling pretty good about this, go ahead and you're good. You're probably good to go. If not, go and stick around for the next one, and we'll go over it together. But it's got a lot of big numbers, and it's a little bit more convoluted. So the problem is actually more simple, but the math is a little bit more crazy. So all right, but let's jump back into this one just to make sure we understand, right? So the first thing we talked about was, okay, a rate of speed is distance over time, right? In this case, miles per hour. So we decided, okay, if in this case we're looking for what is the speed of the river, we're looking for the rate, right? Well, what it's asking us though is if Jake can paddle at a rate of 5 miles an hour, what is the speed of the current of the river? The thing that we can compare is we want to know, like, okay, what does it take for the amount of time of the upstream to equal the amount of time of the downstream, right? That's essentially what we're trying to figure out. And the way we figure out the time is by rearranging this formula, because we know the distances in the rates, right? If we know the distances in the rates, the thing we can set equal is the time. So what we do is we rearrange this formula here so that we have time equals distance over rate. So in other words, the distance over rate of our upstream, we can set that equal to the distance over rate of our downstream, and that'll help us find out what the actual, that will help us figure out what the current is that's pushing us either way, right? So we decided, okay, now let's look at this. So we let the current of the river equal C, and then we said, okay, if we're traveling downstream, that means we're traveling with the current. Like the current is pushing us, it's helping us out. So if that's the case, then it's Jake's rate plus whatever the rate of the current is, right? Like what's the mile per hour, the speed of the current. And then upstream would be us traveling against the current. So we're actually, like, it's going to be harder, right? If you've ever tried to like canoe into or paddling into a current, it's much more difficult. And that would be Jake's rate minus the current. So the river and our rate are kind of pushing against each other. And then what we did is over here, we said, okay, we have the distance and we have the rate, which in this case is speed. The distance of upstream was 6 miles. And the speed of upstream was 5 minus whatever the current was, which we didn't know. And then what we did is we set this equal to, well, first of all, we had to add one to this side, and this may be the confusing part, but the reason why we had to add one to this side is because up here it says, paddling with the current in a river, Jake traveled 16 miles. Even though he paddled upstream for an hour longer than he paddled downstream, so this upstream was included an hour with it, right? This has an hour built into it. So to make it equal, we have to add an hour over here. I hope that makes sense. But that's kind of the idea, is we have to add the extra hour over here because it's built into this number. Okay. And then this part here is going to be our distance over speed, right? But for downstream, our distance was 16 miles because paddling with the current, he traveled 16 miles. And then over 5 plus C, because 5 is Jake's rate, C is the rate we were trying to figure out. Then what we did is we kind of pushed everything down here, found the LCD, made the denominators the same by using the LCD, and of course that means we have to multiply the top by whatever piece is missing. And then from there, we honestly just kind of did a bit of quadratic work. We combined like terms, we set everything equal to 0, and then we went over here, we had c squared plus 22c equals negative 75. We determined that positive 25 and negative 3 multiply to make negative 75, which they do, right? And then positive 25 and negative 3 add to make positive 22, which gave us the answers c equals negative 25, right? Because 0 equals this, we set it equals 0. So c equals negative 25 and c equals 3, which essentially is going to tell us, well, it can't be negative, right? We can't have a negative speed. So the answer had to be 3. All right. Like I said, I know this video has been a little bit long. This problem here, as far as actual like setting up the problem, is a lot easier than this one. This one was very complicated as far as setting it up goes, but then the math itself wasn't particularly complicated. Now this one here is going to be kind of the opposite. The setting up the problem isn't too bad, and if you want to just watch me set up the problem, that's fine. What I'm going to do is set it up, and then if you want to try the math from there, you can. And I'll give you the answer at the end if you want to like try to take a look and see if you can get it. So, all right, let's go ahead and try. All right, so 3 people are planting tomatoes in a community garden. Marta takes 50 minutes to plant the garden alone. Benito takes X minutes, and Tyler takes X plus 15 minutes. If the three together can complete the project in 20 minutes, how long would it take Tyler to complete it alone? Well, we're going to have a problem very similar to the work rate problems we did before, right? Our work rate is going to be the number of jobs we do. So in this case, like how much work we can do over how long it takes us. So in this case, each person's just doing one job, right? They're just planting tomatoes, but it's how long does it take them? So let's look at this. So Marta, we'll go ahead and put the names above them just to like kind of understand where these things are coming from. Takes 50 minutes to plant the garden alone. So it takes, for one job, it takes her 50 minutes. Cool. Benito takes X minutes. So for Benito. So for Benito, it takes him 1 over, well, we don't know how long. It just says X minutes. That's fine. And then Tyler, well, he's definitely going longer than Benito, right? Because he's going to be 1 over X plus 15. Okay. Now, this is all equal to, well, what's the, like, when all three of these people work together, how long does it take? Well, if the three together can complete the project in 20 minutes, right? So it takes, all together, it takes one job, 20 minutes. But you can already see that's going to be faster than Marta, right? So that's good. So this is like the total, right? So together. And then what they want to know is how long would it take Tyler to complete it alone? So we really just need to solve for X and then add 15, and that'll tell us how much Tyler takes. All right. Okay. So if you want to stop here, if you're like, hey, I know how to do it from here, it's just a lot of complicated math, that's fine. I completely respect that. But you're going to be missing out on all the fun. So, all right, LCD. If you want to watch the LCD part, that might be useful because this is a little complicated, right? This is one of those things where 50 and 20, there's not really anything in common. X plus 15, there's not really anything in common. So this LCD is going to challenge you a little bit because it's just all of these pieces multiplied, right? We have 50 times 20. Well, that's a pretty big number. It's 1,000, right? If you want to do like 50 times 20, if you want to write this as 50 times 20, that you can do that. That's fine. And then, well, we have that X, right? And then we also have X plus 15. So this is the LCD, right? We have the 50 and the 20, which is where we get this 1,000. We have the X from down here. It's just 1,000 times X. And then it's 1,000 times X plus 15. So, I mean, if you want to like put the X also in parentheses, you can, right? It doesn't really matter. It's the same concept. Just like I said, you can keep the 1,000 as a 50 times 20, if that helps you as well. But it doesn't really matter either way. All right, so now we have to do each piece, right? And this is where it gets a little complicated because we have to figure out what does the piece already have and what does it need, right? So here on Marta, we already have the 50. So basically we need, if we already have the 50, we need these other three pieces, right? So we need our X plus 15, and our 20. So that's what we're going to have to multiply by the top and bottom. And just to expedite this a little bit, I'm just going to write the numerator because writing this denominator every single time doesn't really do anything for us anyway. So, okay, so we have the 20, right? We have 20, the X, and we have the X plus 15. Okay, and that's Marta, okay? So now let's do Benito. Benito has the X already, so we need everything else. We need the 1,000, we need the X plus 15. So plus 1,000 times X plus 15. All right, now Tyler already has the X plus 15, right? So if Tyler has the X plus 15, we just need the 1,000X. So plus 1,000X. All right, cool. So now we have, the last one is 1 over 20. We already have the 20, so we just need the other piece, which is the 50, right? Because the only other number is the 50. So this is going to equal, right? Again, we don't need the 20, we just need 50 of it. So 50X times X plus 15. Okay. We're just getting started. All right. So this is just a bunch of X's and numbers, right? We can simplify all of this. And we want to set up a quadratic function that is set equal to 0. And we want to go through all that stuff and see what we can do. So let's go and give it a shot. So let's do it. 20x times x plus 15 is going to be 20x squared plus 15 times 20 is going to give us 15 times 2 is 30. So 300x plus, let's do this. So 1000x plus 15,000. Just, normal math numbers here. And then plus 1000x. And this equals 50x times x is 50x squared. And then 50x times 15 is 5 times 15, which is 45. No, 75. So plus 750x. All right, excellent. Let's keep going. So now we just have to combine like terms. Okay. We have an x squared over here. There's no other x squareds. We have a plus 300x. We have a plus 1000x. And we have a plus 1000x. Okay, so those are the only pieces that are in common. Cool. So we have 20x squared plus, was it 2300x? All right. And then, let's see, plus 2300x plus 15,000 equals, well, okay, 50x squared. This is one of those problems where you should probably just write it out just to not make any mistakes. Plus 750x. All right, minus 50x squared minus 750x, because remember we're trying to set everything equal to 0. So over here we have minus 50x squared. And then what was this? Minus 750x. So minus 750x. Let's go ahead and add everything here. So 20 minus 50 is negative 30x squared. And then we have 2300 minus 750 would give us 1550. So plus 1550x, and then plus 15,000 equals 0. So you can see this is just, your regular everyday fun problem. All right, and now what I'm going to do is I'm going to set this, I'm going to get this x squared to not be negative, because that'll make our life a lot easier. And so we're going to get we just basically multiply all of this by -1, right? Multiply both sides by -1. So we have 30x squared minus 1550x, and then minus 15,000. Okay, and this equals 0. Now, anytime you have huge numbers like this, I'm just telling you, the easiest way to do it is just quadratic formula, right? If you want to try to figure out 30 times 15,000 and then find the factors that work for that, you absolutely can. Go nuts. You know what I mean? I'm not going to stop you. By all means, have your fun. But what I would strongly recommend is just to kind of plug this into the quadratic formula, and that's what I'm going to do. I'm just going to plug it into the quadratic formula, and I'll let you guys do all the math and plug it into calculators if you want to do all that. But this is basically how you do it, right? Once we get to this step, it's just a matter of using something you've used 1,000 times. So it would be x equals negative b, right? So negative, so it would be 1550, right? Because negative, okay, yeah. Plus or minus the square root. These are going to be huge numbers, so I'm going to make this kind of long. B squared, so negative 1550 squared, and that'll end up being a positive number, right? Because you squared it. B squared minus 4ac, so 430. C is negative 15,000. And then, of course, all of that over 2a, which is just 60. Yeah. So, like I said, if you want to plug this all into your calculator and have fun with it, you can go ahead and do that. Otherwise, you can drop out. I completely understand. But yeah, I'm in it for, I mean, we've already got this far, right? All right, so 1550 squared. All right, so 1550 squared is 2402500, and then minus, so we have 4 times 30, 4 times 30 times 15,000. So 1,800,000. And of course, there's two negatives in here, right? There's a -4 and a negative. So this is actually going to be plus 1,800,000. Okay. So the square root of all that, perfectly normal numbers, right? So let's go and add our number there. So 24,002,500. And we get square root of 42,02500. And if you take the square root of that, it's actually a perfect square, which is kind of cool. So I've got 1550 plus or minus, and that ended up being 2050 over 60, right? We're almost there. We're so close. All right, so 2050 plus 1550 is 3600. Oh, this is really cool. So this is 3600 over 60. The other one's going to give you a negative number, right? And we're dealing with a problem where we're talking about how long does it take. So our x, we can't have a time that's negative, right? So this is going to be our answer. It's going to be the positive version, right? We might as well not even do the negative because we're going to get a negative number. That just doesn't make sense. So 3600 divided by this, we can cancel out the zeros, and we're going to get 360 divided by 6, which is just 60, right? So here is 60. So x equals 60. Out of all of this, we decided x equals 60. Let's go back up here. It's always nice when the math works out. I'm ecstatic. So if x equals 60, how long does it take Tyler to complete it alone? 75 minutes. That's amazing. We did it. All right. So if I were you, if you really want to take away the steps from all the problems that we did today, we did a lot of math. But if you really want to go over the steps, the one I would do here is identify extraneous solutions. It gives you a step-by-step breakdown of what to do. I'm tired of talking. My voice is getting tired. I'll see you guys in the next unit, and we'll see you for Unit 5. Have a good one.